Good morning, students. Let's talk about gas laws. First, we tackle about the kinetic molecular theory, wherein particles in an ideal gas have no volume, they have elastic collisions, meaning to say the molecules bump to each other, and they are in constant random straight line motion. They also don't attract or repel each other, and the average kinetic energy is directly related to Kelvin temperature. Here are the characteristics of gases. Gases expand to fill any container in a random motion and no attraction. And gases are fluids, just like liquids, and gases have very low densities. Gases can be compressed. Solids cannot be compressed, as well as liquids. Gases undergo diffusion and effusion. Later, we will discuss about the difference of effusion and diffusion. The first variable that we're going to tackle when we're talking about gas laws is a temperature. We always use absolute temperature, which is in Kelvin when working with gases. We all know that the formula for absolute temperature is degrees Celsius plus 273. And for us to convert Fahrenheit to degrees Celsius, that is Fahrenheit minus 32 multiplied to 5 over 9. Another factor when we're studying gases or gas laws, we have pressure equals force per area. So which shoes do you think create the most pressure? Definitely this one, because it has less area, therefore it has greater pressure. There are key units for pressure. For example, we have this 1 atm, 760 millimeter mercury, 760 torr, 14.7 pounds per square inches. Now, once we say STP, talking about standard temperature and pressure, which is for the temperature, we have 0 degrees Celsius or equivalent to 273 Kelvin, and for standard pressure, that is 1 atm, which is 101.325 kilopascals. Let's tackle now gas laws. We have the Boyle's law, Charles' law, and the Gay-Lussac's law. As what you could recall, for the Boyle's law, we have inverse relationship wherein P and V equals to K. Once we say inverse relationship, they have the product of pressure and volume is constant. So this will be the graph of pressure and volume. The pressure and volume of a gas are inversely related at constant mass and temperature. Now for Charles' law, direct proportion, as we increase the volume, the temperature will also increase, and therefore the ratio is a constant. So this will be the graph of a direct proportion. The volume and absolute temperature of a gas are directly related at constant mass and pressure. For the Gay-Lussac's law, we have temperature and pressure, wherein as the temperature increases, the pressure will increase. The pressure and absolute temperature of a gas are directly related at constant mass and volume. PV is equals to K for the Boyle's law, V over T for the Charles law, P over T for the Gay-Lussac's law. Combined gas law we have is this, PV over T. And therefore we could write it as P1 V1 over T1 equals to P2 V2 over T2. This is the formula that you should recall. Once we say ideal gas law, an ideal gas exhibits certain theoretical properties and obeys all of the gas laws under conditions. We assume that the gas does not condense into a liquid when cooled. So let's try to visualize how this gas law has been formulated. An ideal gas exhibits certain theoretical properties wherein gas is at standard condition in 1 mole. Therefore, once we say standard condition or the STP, the pressure is at 1 atm, the molar volume of a gas is at 22.4 liters. The temperature is 273 Kelvin. So changing pressure into 1 atm, changing the volume of the gas into 22.4 liters divided by 1 mole, and for the temperature, which is 273 Kelvin, therefore 22.4 divided by 273 Kelvin will yield us 0.0821 liter atm over mole Kelvin. So this 0.0821, this will be represented as R. Creating now our ideal gas law formula. Okay, so we have N2 multiplied to R multiplied to T2. Therefore, we have an ideal gas law formula which is known as PV is equals to nRT, where R is equals to 0.0821 liter atm per mole Kelvin. This value of R is being derived from 22.4 divided by 273, and sometimes this unit is not given, but rather we have 8.3 joules per mole Kelvin, or this joules per mole Kelvin is just equal to liter multiplied to kilopascals per mole Kelvin. So this will be always given in the exam, or sometimes 0.0821 is also given. Take note, the formula is PV is equals to nRT. Another law that we have is the Graham's law. And once we say diffusion, it is the spreading out of gas molecules throughout the container until evenly distributed. For the effusion, we have passing of gas molecules through a tiny opening in a container. For example, this diffusion process wherein compare hydrochloric and ammonia, which one will diffuse faster. So, computing for the molar mass of hydrochloric, hydrogen is 1, chlorine is 35, this one is 36 grams per mole. NH3 we have here 17 grams per mole, and then therefore the heavier is hydrochloric, therefore it travels lesser as compared to NH3. Lighter gas moves faster, meet closer to heavier gas. This is what we've known as Graham's law of diffusion. Graham's law states that the rate of diffusion of a gas is inversely related to the square root of its molar mass. So this is the equation. Now, if we are asked to compare or determine the relative rate of diffusion for krypton and bromine, solving for their velocity, we can see that krypton diffuses 1.381 times than bromine. How about if we compare for hydrogen and oxygen? We all know that hydrogen will diffuse faster than oxygen. The hydrogen's velocity is 49 meter per second, while for the oxygen we have 12.3 meter per second.